Alrighty, this is my explanation of the sample Circuit Jamboree Take AP2. So I'm going to go through all 8 of these, explain them a little bit. Hopefully my work can help with that, but if you want me to give some verbal solutions, I'll be happy to do that as well. So for number 1, and actually for all of these, I think redrawing the circuit is extremely important, and often multiple times. So to get the total resistance, which is how we've got to attack these circuits first, we're going to combine these two 8 ohm resistors in parallel using the rule for parallel resistance. 1 over 8 plus 1 over 8 equals 1 over R. R, that's total is 1 over 4, so R is 4 ohms. So this is a circuit with a 4 ohm equivalent resistance here and a 4 ohm individual resistor there. That gives us a total resistance of 8 ohms. Using Ohm's law, which is up here, and if you remember, Ohm's law works for any whole circuit or any part of a circuit, but you do have to be careful to make sure you're using the correct values for whatever whole or part of a circuit you are thinking about. So we'll do 16 volts divided by 8 ohms. That gives me 2 amps total current. That's also the current going through the 4 ohm resistor, since the circuit is a series circuit at that point. Here, because these have equal resistance, the circuit is going to have the current split, so we're going to have half the total, or 1 amp, in each of these branches. The voltage across the 4 ohm resistor here, that current times 4 ohms, so 2 amps times 4 ohms is 8 volts. We would have 8 volts also across each of these. Why? 1 amp times 8 ohms in each branch gives us 8 volts. Total power in the circuit, well, you could do I squared times R, so 2 squared times 8, 4 times 8, that's 32 watts, or V times I, that's 16 times 2 is 32 also. Going to number 2, we end up having this one. We've got these two resistors in series up here. I'm going to simplify that first into a single 12 ohm resistor, and then this really just becomes a parallel circuit with a branch with a 2 ohm resistance, 4 ohm resistance, and then this top one has a 12 ohm resistance. So overall, to get the total resistance, 1 over 12 plus 1 over 4 plus 1 over 2 equals 1 over R. That total resistance is 1.2 ohms. Using Ohm's law, V divided by R gets me 10 amps for the total current. That's the total current going through this spot, the total current going through this spot, but not the current in any of these branches. So the next thing I did is I solved for this one, which is all by itself. I could have also done the 2 ohm one. It doesn't really matter. But here, in this particular path, the 4 ohm resistor has no other resistors in that path for a particular electron that chooses that path. The same thing with the 2 ohm resistor. So all 12 volts must be used up or converted into heat energy from electrical potential energy across the 2 ohm resistor, and all 12 volts would be used across the 4 ohm resistor. Remember, voltage is energy per charge, so it's not like it's wrong to say it's all used up. It's in any path, all the energy per charge must be converted. So these are each 12 volts. To find the current through them, pretty simple. 12 divided by 4 ohms in that branch is 3 amps. 12 divided by 2 ohms is 6 amps in that branch. Now the nice thing you could think about is you could also then go up here and attack this. And I could say, well, I know across this entire branch up here, and I'm looking at this diagram now, I've got 12 volts and I've got 12 ohms. So 12 divided by 12 is 1 amp. So I have 1 amp going through each of these two resistors because they're in series with each other. And resistance in a series circuit or a series part of a circuit is the same. Now to go back here, and I did finish off with this, the 1 amp times the 7 ohms of resistance gives me 7 volts and 5 volts across the 5 ohm resistor. And notice that does equal the full 12 volts, which we said we would have to have across that top branch. The total power dissipated here is something I did not answer properly, so I will have to do that now. That's going to be equal to 10 amps multiplied by 12 volts, or 12 volts times 10 amps, that equals 120 watts. Move that over here. I'm going to shrink that down, change the color to green. That way people who don't listen to this will think, wow, he did that all by himself, blah, 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 blah. And it doesn't look great, but you get the idea. Okay. For this one, I think this was a fairly challenging one. I think this was the most challenging one. So up here, to get the total resistance, I have a couple redrawings. These two parts are in series with each other, so they're a combined total of 30 ohms. So I redrew this as 20 ohms at the top, 8 ohms at the bottom, 20 ohms in this middle branch, 30 ohms in this outer branch. So now these are in parallel with each other. I take 1 over 20 plus 1 over 30 equals 1 over R. The resistance of this whole part is 12 ohms. I redraw it again. So I have the 20 ohm resistor up here, the 8 still down here. They're all by themselves. All this mess of these three is now equivalent to a 12 ohm resistor. So now it's easy. 20 plus 12 plus 8 gives me 40 ohms of total resistance. Total current, 12 volts divided by 40 ohms is 0.3 amps. So 0.3 amps is leaving the battery here and going through here. 0.3 amps is going through this resistor here and going back up through the battery. However, that 0.3 amps is going to split when it comes to this middle branch and this outer branch. So the total current of both these branches should equal 0.3 amps. It could never be more than that. So the first thing I would do is recognize that, hey, the current through this is 0.3 amps, the current through that's 0.3 amps. So that's easy. The next thing I do is I figure out the voltage used across these. So 0.3 amps times 8 ohms is 2.4 volts. 0.3 amps times 20 ohms is 6 volts. So of my 12 volts across this top and bottom resistor, I've used a total of 8.4 volts. I have 3.6 volts left. And since if you look at this path with this middle branch, that resistor is all by itself, that means that would be 3.6 volts across that. I don't know if you want to necessarily solve it that way or not, but you could. And that's how I did it right here. The other way you could think of is think of this simplified drawing. All this mess is equivalent to 12 ohms. All this mess has equivalent of 0.3 amps going through it. 0.3 times 12 is 3.6 volts. So that was the third thing I did. The fourth thing is over here. Once I have the voltage of that branch and I know the resistance of that branch, I can divide that out with Ohm's law and get the current through that branch. So the current through this branch is 0.18 amps. The next thing I did is I figured out the current through this outer branch. Well, if the current coming into this junction here from the left is 0.3 amps, and I have 0.18 amps going down this middle branch, then I have 0.3 minus 0.18 or 0.12 amps going through the outer branch. There would be other ways you could solve that. For example, you could have 3.6 volts divided by 30. That would give us 0.12 amps also, because the voltage across each of these branches is equal to the voltage across the whole component, since they're in parallel with each other. And voltage divided by resistance of the branch would give me the current in each branch. So 3.6 divided by 20, 3.6 divided by 30. Either way, the current through this 15 ohm resistor and this 15 ohm resistor would be 0.12 amps. And now I can go back here and say what's the voltage across those resistors. Just take the current and multiply it by the actual resistance value. So that's what I did last, and that's 1.8 volts. Number 4, this is my simplified diagram. 1 over 3 plus 1 over 6 equals 1 over R. This is equivalent of a 2 ohm resistor. 2 plus 2 plus 4 is 8 ohms total resistance. 24 volts. 24 divided by 8 is 3 amps. The current through I1 and the current through I4 are 3 amps. This one you could figure out a couple ways, but if this side has half the resistance of the right side, then twice the current would go through here as compared to here. Since we have 3 amps total, 2 amps goes through the left side, 1 amp would go through the right side. Or you could figure out that this is an equivalent 2 ohm resistance. We have total 3 amps. That means the voltage across this whole spot is 6 volts. So the voltage across R2 and R3 would be 6 volts. 6 volts divided by 6 ohms in this branch gives me 1 amp. 6 volts divided by 3 ohms in this branch gives me 2 amps. So that's kind of how I'd figure that out. V1 and V4 are pretty easy. Five is something I talked to a few people about. I would attack this middle part first. Those two resistors are in parallel with each other. So I figure out that that has a total resistance of 4.24 ohms. I redraw the circuit. So A and B, this 20 ohms by itself, this 3 ohms by itself. I've solved this for a 4.24 ohm equivalent resistor. This is still a 10 ohm resistor. Well, it is now because I had 6 and 4, which are in series with each other. So now I can put those two in parallel and solve that the equivalent resistance of all this, which in reality is all this, is 2.97 ohms. 1 over 10 plus 1 over 4.24 equals 1 over R. Down here, I'm going to redraw for a second time, so that's my second redrawing. I have 3.0 ohms up here. All this mess became 2.97 ohms. 3 and 2.97 are in series with each other, so that's 5.97 ohms. So now this last redrawing says this middle part is 20 ohms, which has always been, and all this mess over here has been simplified to 5.97 ohms. So 1 over 20 plus 1 over 5.97 equals 1 over the total resistance. That comes out to 4.60 ohms. So to refresh, I started here, simplified this, then simplified these, redrew again and simplified those, and now I've got a simple parallel circuit with two resistors in parallel. On to number 6. So here are my drawings. This one can be a 3 ohm resistor, this could be a 6 ohm resistor, so I made that 3 and 6. The equivalent of all this mess up here, which is really all this mess of these 4 resistors up here, is 2 ohms. 1 over 3 plus 1 over 6 is 1 over 2, so it's 2 ohms equivalent. So the whole circuit has 4 plus 2, or 6 ohms of resistance. V divided by R, 12 volts divided by 6 equals 2 amps. I'm doing this first. So the V across the 4 ohm is 2 amps times 4 ohms is 8 volts. The current through that would be still 2 amps. Now I'm going to pick on the branches. So I did this top branch first. So the way that I thought about it was this whole thing has 2 ohms. The whole current is 2 amps. So the voltage across this whole component is 4 volts. But in this branch, that 4 volts divided by 3 ohms gives me my current. So 4 divided by 3 is 1.33 amps in that top branch. 4 volts divided by 6 ohms gives me 0.667 amps in the bottom branch. Lo and behold, the current in this top branch and the current in this bottom branch should add up to the total current, which they do. Now, I'm going to end up doing this last. This one is I did not really do last. It was at the same time as the 5 ohm one. So with this, now I know the current through the upper branch, so I just multiply it by that resistance, and then I multiply it by that resistance. That gives me the voltage across each of them, 2.67 and 1.33 volts respectively. And then the 0.67 amps multiplied by the 5 ohms would give me this amount. Or I could say 4 volts minus, actually I couldn't do that, I didn't find the voltage on the downward one yet, so this would be 0.67 volts. So here, again, there's ways you could work through that proportionally, but I probably should have shown here, this is 0.67 amps times see if I can find the keystroke for ohm. Oh, I did. That's right there. Actually, that's a lie. That's 0.67 amps. Times 1 ohm. Okay? So that's how we would do that. Going to number 7 and 8. 8 I think is actually not that complicated, but it's interesting. So for number 7 here, simplifying this first, 1 over 40 plus 1 over 24 gives me, surprisingly, normal answer of 15 ohms. This 15 and this 15 then are in series, so that's a 30 ohm total resistance for this top part of the circuit. These, 1 over 9 plus 1 over 18, 6 ohms for this bottom part. So I could figure out the total resistance, 1 over 30 plus 1 over 6. It's 1 over 5. Therefore, this is a 5 ohm total resistor. If I wanted to ask you more questions about it, like this, I could figure out the current through this one would be whatever the known voltage would be divided by 18 ohms. The known voltage would divide by 9 ohms, but we're not given a voltage here. So no worries. Oh, but I am asking that now. So if there's 4 amps going through the 9 ohm resistor, 4 I times R is 36 volts. So the power source must be 36 volts. And now I could use that to figure out the fact that there would be 2 amps going through here, and in this total top part up here, 36 volts divided by 30 ohms would give me about 1.2 amps through the top. Last one, power source is hooked to 4 identical light bulbs. It's like this. This is the brightest. It gets all the current. And if it has the same resistance, more current times the same resistance gives us more voltage across this. When the current splits, more current goes in this top branch because there's less resistance than down here where we have 2 identical bulbs. Each would have resistance adding to each other because they're in series with each other. So R2 would be the next brightest. And then finally, R3 would equal R4, but they'd be the dimmest. If we remove bulb 1, in other words, that is just simply gone, gonzo, and the circuit was open, all these would go dark because there's no path for the electricity to flow. If I simply remove bulb 2, pulled that out of the circuit, bulb 1 would get dimmer, and bulbs 2 and 3 and 4 would get brighter. Why does bulb 1 get dimmer? Well, it gets dimmer because now I'm in a series circuit, and therefore the total resistance with only one path for the charges to flow would actually increase. Bulbs 2 and 3 get brighter because before the current was split between the top branch and the bottom branch. And although the total current is less now, all that total current is going through this bottom part since R2 has been pulled out. So therefore, these bulbs would get brighter. If I remove bulb 3 here, bulb 4 would obviously go out because it's in the same path and in series with bulb 3. Once again, I basically just made a series circuit with R1 and R2. R1 would get dimmer because the total resistance has increased now that we have a series circuit instead of a parallel circuit. And R2 would increase because now all that total current, even though it's a bit less, would be going through R2, so it would brighten. So I hope this helps understand these. You can listen to this or just watch me going over them as much as